So we've been talking about using factoring to solve quadratic equations because we can exploit the zero product property. Now, we typically only need to use factoring if we have multiple variables of x's. For example, I would use factoring to solve equations like x squared minus 6x equals 0, x squared minus 5x plus 6 equals 0, 2x plus 5x minus 3 equals 0. Notice in each of these three generic quadratic examples, there are multiple terms of x's. That is to say, there should be a squared here. That is to say, each equation has a squared term and an x term. Here's my x squared term, here's my x term. Here's my x squared term, here's my x term. X squared and x. So when you have multiple terms of x's, factoring is one technique to go. But it turns out that if you only have one term of x, you don't need any fancy tricks. You can just solve it straight up using regular algebra, using inverse operations. Well, if I have an x squared equation, I'm eventually going to have to use the opposite of a square, which is a square root. So that's sort of the whole point of this section, is that if you have equations that you're supposed to solve and you only have one x squared term, you can bypass any fancy tricks and just solve it directly using square roots. Well, it sort of makes sense that before we use square roots to solve, we should probably be proficient with radical expressions. To start off, let's just do a quick summary of some vocabulary words that we should have by now, and if we don't, here's a nice refresher. Right. The first vocab word is radical. I'll be using this term a lot, and a radical is nothing more than an expression of the form square root of x, or s, excuse me, where s is a number or expression. In this definition, I used a square root, but it could be a cube root, a fourth root, a fifth root, whatever. It's what we call a radical. What we call a radical is this whole symbol here. So any expression that has that symbol, we call it a radical. Well, radicals have this thing called radicands. And a radicand is simply the stuff. And yes, that's very technical, proper math terms. It's the stuff inside a radical. Now, typically with radicals, we talk about this thing called a conjugate. Now, a conjugate, and conjugates only exist for binomials. A conjugate is, for any binomial, a plus b, the conjugate is the expression a minus b. Basically, what a conjugate is it's his evil twin. It's the identical expression, except the middle sign has changed. Okay. Now, since we're going to be using square roots specifically to solve equations, we should be familiar with a couple of properties of radicals. I like to call these the gluing and ungluing properties of radicals. The formal names: properties of radicals. The formal names are called the product property, which basically says if you have two separate square roots and you're multiplying them, you can squish them together as one giant square roots. Of course, you can go forwards and backwards. If you had one giant square root, you can break them apart into two separate square roots. We also have this thing called the quotient property, which basically says the same thing except with division. If you're dividing two radicals, that is equivalent to one giant radical of a fraction. And of course, you can read this forwards and backwards. If you have a radical of a fraction, you can split them apart into two separate radicals. This allows you to simplify radicals, provided you know your multiplication tables, your times tables. So for example, suppose, let's delete this guy here. He can stay, I can't delete him. Suppose you had the square root of 24. Now, to simplify radicals, all you have to do is break down radicals into factors. Now, ask yourself, what two numbers multiplied together equals 24? And there are lots of different ways you can do this. There isn't no one set way. Off the top of my head, I know that 6 times 4 is 24. What you want to do is keep breaking down these numbers until you reach prime numbers. For instance, I know that 6 is the same thing as 2 times 3. Notice what I'm going to do is when I split numbers, I like to cross them out so I don't double count them. And I know 4 can be split into 2 times 2. What you want to look at next is duplicates. Are there any single numbers that repeat or appear more than once? In this instance, I have 2 2's here. Actually, I'm going to color code this. I have 2 2's here. So that means my original radical, radical 24, is equal to a single 2. Do I have any numbers that are left over? I have a 2 left over and a 3 left over. Those are the numbers that I did not circle. Any numbers that are left over goes back inside of the radical. And remember that everything is multiplying each other. So, ultimately, overall, what does the radical 24 equals? It equals 2 on the outside, radical 6 on the inside. This is the simplified form of radical 24. You can utilize this idea for both whole numbers and fractions. For example, if I wanted to simplify the square root 9 over 64, I just have to remember that a square root of a fraction is the fraction of the individual square roots. And then, of course, radical 9 and radical 64, since they're perfect squares, should be easy for us to figure out. That's simply 48. Radicals become a little bit tricky to handle if you do not have a perfect square in the denominator. So how do you simplify radicals when there aren't perfect squares in the denominator? If there is not a perfect square in the denominator, you must, and this depends on what you have in the denominator. If you have a monomial in the denominator, you're going to multiply the numerator and denominator by the denominator. If you have a binomial in the denominator, you're going to multiply the numerator and denominator by the conjugate, that's one of our vocab words, of the denominator. Now, if you're reading these two definitions and reading these two techniques and you're still going, what does this mean? How do I utilize this? I think examples paint the picture a bit more clearly. So let's do an example of each. Suppose I ask you to simplify the square root of 7/3. Okay. Well, according to our gluing and ungluing properties, if instead of taking a square root of a giant fraction, you can split them apart into separate square roots. Now, 7 is not a perfect square, and 3 is not a perfect square. So there's nothing I can evaluate at this point. But I still have a radical in the denominator, and I wanted to get rid of him. Well, notice what I have in the denominator. I just have a single piece. There's only one radical. I don't have any pluses or minuses elsewhere. It's simply a single radical 3. So this is an example of a monomial in the denominator. And according to the procedure, according to the technique, if I have a monomial in the denominator, I just have to multiply the top and bottom by whatever's in the denominator. So in this instance, in this example, what is it that I'm trying to get rid of? I'm trying to get rid of radical 3. So let's just go ahead and multiply the denominator and the numerator by radical 3. When I do this, apply the property, radical times a radical, you can squish them together as one radical. So 7 times 3 is 21. And then in the denominator, radical 3 times radical 3 is radical 9. And 9 is perfect, so we should know that radical 9 is a plain old simple 3. Okay. Then, of course, on the side as scratch work, I try to figure out if I can break down 21. I'll just save you the trouble. If I fast forward through this, radical 21 can't be simplified, so that is our final answer. What if I have a binomial, right? So what if I had something like this? I wanted to simplify 4 over 5 plus rad 3. So in this case, I hope we notice that we do have a radical in the denominator, so that's something we have to take care of. But notice what's in the denominator. I have two pieces here. I have a 5 separate, and I have a radical 3 separate. So this is a binomial situation. And according to the technique, according to the idea, if I have a binomial in the denominator, I'm going to multiply the numerator and denominator by the conjugate of the denominator. And conjugate is simply a math term for the opposite binomial. Basically a clone of the binomial, except the middle sign is changed. So in our example, since I have a binomial in the denominator, I'm going to multiply the top and the bottom by the conjugate. And the conjugate of 5 plus radical 3 will be 5 minus radical 3. It literally is the same binomial, except the middle sign is changed. Now in the numerator, you can just do regular FOIL, regular repeated distribution. So that's 20 minus 4 rad 3. And of course, we can go ahead and FOIL out the denominator. But you have to remember our special factoring pattern. Remember how we said if you multiply two conjugates, a minus b times a plus b, you do not actually have to FOIL because the middle terms will always cancel out. That simply equals the first guy squared minus the second guy squared. So to do the denominator, sure, I can go ahead and do all the work. 5 times 5 times radical 3 times 5, so on and so forth. But I could just go ahead and know that the denominator is going to be the first guy squared, 25 squared. It's always going to be a minus the last guy squared. And radical 3 squared is just 3. Let's go back to the yellow guys. Sorry, 5 squared is just a regular 25. He's not 25 squared. That's why I deleted the square. And then the rest is just math. 20 minus 4 radical 3 over 22. When it comes time to simplifying these expressions, you always want to look at the outside numbers. Don't get so focused on the inside numbers. And you have to look at all of the outside numbers at the same time. It's all or nothing. I asked myself, is there a number I can divide out from 24 and 22? Of course, the answer is yes. I can divide everything by 2. So my final simplified answer would be 10 minus 2 rad 3 over 11. So the bulk of this practice will be simplifying radical expressions, but of course, I want you guys to be able to be proficient in solving radical equations. And again, the idea is that we typically use a radical if there's only one variable term. For example, suppose I ask you to solve 1/4 x minus 6 squared equals 8. This is technically quadratic because I have a variable squared, but notice, I'm only going to highlight the variable. There we go. How many things did I highlight? There's only one. So when there's only one variable term, you don't have to do fancy tricks like quadratic formula or completing the square or factoring. If there's only one variable term, you just solve the variable using regular algebra. To solve for x, we need to get rid of the 6, the 1/4, and the square. So hopefully we're a little bit proficient at algebra. The first thing I want to get rid of is the 1/4. So the first thing we're going to do is multiply both sides by 4. That's the reciprocal, or that's the inverse of a 1/4. These guys are gone. So what's left with is an x minus 6 squared equals 32. The next step is to get rid of the square root. So I'll go ahead and square root both sides. And this, if you're going to make a mistake, is where you're going to make a mistake. You need to remember, whenever you take a square root to solve an equation, your result will be plus or minus. Because we know when it comes to radicals and square roots, if you square a positive number, say for example you square a positive 3, that's the same thing as squaring a negative number. For example, if you squared a negative 3. So anytime you're taking a square root to solve an equation, you have to know whatever's over here is going to be positive or negative. So I'm going to have plus or minus the square root of 32. That's where the asterisks come. And then of course we can see it's very easy from this point on to get x by itself. We have to get rid of the minus 6. So the opposite of a minus 6 is a plus 6. I'm going to add 6 to both sides. Now when it comes to numbers with plus or minus, I always like to write the plus or minus term at the end. So I'm actually going to write the 6 first, and then the plus or minus 32 at the end. Is that our final answer? You always want to simplify it as much as possible. So as scratch work here, I want to see if I can simplify the square root of 32. So let's break them down. I know that's 8 and 4. I know that's 2 and 4. I know that's 2 and 2. 2 and 2. You want to highlight the doubles. So I have a double here. I have another double here. And I have this 2 here left over. This 2 here left over. So radical 32 is the same thing as 4 radical 2. So our final answer is 6 plus or minus 4 radical 2. Let's just do one more example so you do have one example. Let's say I ask you to solve 2x squared minus 16 equals 34. Again, please recognize that this is a quadratic because we have an x squared, but I'm just going to highlight the variables. There we go. How many variables did I highlight? Just one. If you only have one variable term, this is the whole idea of this lesson. You don't need any fancy tricks. Just use good old-fashioned algebra. So I hope we can see that to get the x by itself, we need to get rid of the 2, we need to get rid of the 16, we need to get rid of the square. So just do regular algebra. The first thing we will do is add 16 to both sides. I think this used to be a 34 here. I erased too much. There we go. That's 2x squared equals, what's that? 34 plus 16 is a 50. Divide both sides by 2. That's going to be x squared equals 25. And the last step is to square root. And remember, anytime you take a square root, your result will be plus or minus. And the square root of 25 happens to be 5. So that's basically the idea. When you solve quadratic equations, we typically use factoring. That's what we did in 4.1 through 4.3. But the idea of this lesson is that if you only have one variable term, you don't have to do anything fancy. Just go ahead and solve for x directly using good old-fashioned algebra, using good old-fashioned inverse operations. That is 4.4.